showing up. No, that's not calculus. Ha! Yeah, they're joining. Nice. Finally got it to work. Welcome, everybody. Keep coming in. I'm going to let the students come in. We're having some technical difficulties. Somebody say something in the chat if you can hear me. Can you all hear me? Someone answer. Can you all hear me?
I can.
Okay. We're gonna have to figure this out, guys. I just heard someone answer me. It must be.
Yeah, I can also hear you, if that helps.
You're Cody?
Yes.
Okay. All right. Thank you for answering. Okay. I am muting everyone. So if you've been muted, that's okay. Don't worry about it. What I would like is for you all to correspond with me right now in the chat. Can anybody write something in the chat? There we go. Good. All right. I'm starting to figure this Zoom thing out. Okay. So now I'm just allowing people to come into class. For some reason, I keep having to manually admit everybody. There's like a waiting room, and then I have to manually admit people. Okay. All right. There's some discussions in the chat going on. That's good. Okay. So everybody, if you're wondering what's going on right now, I'm just kind of waiting for everybody to join class. Yeah, get to know each other. Good job, Joe and Albert and Janice and Cody. Drexel. Yeah, let's go. Let's go. Good evening to you. Who said good evening? Brittany, good evening. Hi, Elizabeth. Sup, Joshua. Hey, Vanessa. Hi, Zoe. Hi, Anthony. Hello, Derek. Or Drexel. There we go. Very good, very good. Doing really good. How are you? Okay, good. All right, so this is good. We're corresponding here. Hit admit all. I don't know why I'm having to like manually admit people. I'm hoping to set this up somehow to just have it to where you just join. I don't know why there is a waiting room. I'm probably gonna have to fiddle with the settings so that there's no more waiting room. That's not cool. You shouldn't have to be in a waiting room. You should just be able to join automatically. So yeah, probably the first 15 minutes of class will be us trying to set Zoom up. But after that, we're gonna start going real fast. So let me just keep adding people on here, allowing people in. I believe I have in this class, I believe there's 33 of you, and I only see 18 participants. That may not be a bad thing. That just might mean that that's all the people that are available at this moment, which is fine. Admit all. Okay. Increasing the number of individuals. Hello. Hello, everybody. Janice. Jay. Okay, I won't call you Jay. Tired. Long night and day at work from Joe. Okay. Well, right now, you guys just start getting to know each other during chat while I get everybody from the waiting room to come in. And then we will continue on lecture once we get that started. Okay? I will ask you guys, have you done the pre-assessment assignment yet? That is in your modules. I see a yes, that's good. Good. That was due, okay? I believe that's due midnight. So you need to get that done. It's not for a grade. Good. Good. I see people saying I just did it. Good. It's not for a grade, but it's for our department to be able to assess where generally you all stand. How much math do you remember from the last time you took it? That's what we just want to know. Really. Admit all. Okay. So we're getting more and more individuals to show up. You'll get it done by midnight. Okay. Good, good. Elijah likes the tie. Thank you. It's got mathematics on it. Right there, that's the presence of a gravitational mass causing curvature in space and time, creating a singularity or event horizon, and that's a black hole. What does everyone do for a living? That tie is pretty lit. Thank you, Janice. My wife got it for me. Okay. All right. Okay. We got more people in the waiting room. Okay. So I'm going to wait 2 more minutes. I'm going to wait 2 more minutes while I keep letting people in. And then once that's done, I'm going to start lecturing, and I'll just keep noticing if people are entering or not. There's probably a better configuration to where I don't have to do that. People can just click and join, and they don't have to do the waiting room. Okay? Okay. Let's see. Good morning from Target. Video feed. College is rough. Working for construction. Anytime. Yeah, that's good. Everybody get to know each other right now. I love that. Let's get to know each other. We're trying to simulate reality as much as possible here. Yeah, just kind of chat with each other until I can get all or most of the students here, because I'm having to manually allow them to come in to the Zoom conference meeting. So I believe we got the majority of the students here to do so. Let's see how many individuals are supposed to be. There's about 39 students in this class, so let's see how many of you guys have shown up. We got 24 participants, so a few people have not shown up. So I'll just be on the lookout right now. The clock strikes the time where I'm no longer going to wait to click people in. I'm just gonna peer at my screen every now and again. And if there's individuals in the waiting room, I'll let them in. Okay. And now we're gonna get started. So my name is Professor Niazi. This is Pre-Calc 1. And we are going to be talking about section 1.1, 1.2, 1.3, 1.4, and 1.5 in your textbook. Okay. Just a quick note on the importance of mathematics. You may be in this class because it's a general education course. You may be in this class purely because you're being forced to. I got to take my math class. I got to do this and that. Most people are not in here on their own accord, and it is my experience, my personal experience, and everyone's really personal experience that math is some subject that they don't like. It was my personal experience. I obviously like math. That's why I teach it. But I aspire to install an appreciation for mathematics in this class for you guys. And here's how I'm going to do it. I'm going to explain to you why math works the way it does. I'm not going to tell you this is the formula, just use the formula. I'm going to show you why is the formula the formula. I'm going to tell you why you can't divide by 0. I'm going to prove it. I'm going to explain why you can't. I'm going to show you why any number raised to the 0th power is equal to 1. I'm going to rigorously explain and prove all of the things in mathematics in which once you were taught it, you were probably curious, why is that the case? And you ask your teacher, or maybe you were too shy, so you just wondered it, you never asked, but you asked your teacher, why is like the area of a triangle 1/2 base times height? And they said, well, that's just a formula. And if you didn't accept that as an answer, well, you were being rude and disruptive. But in this class, that is not the case. You will get thorough justification as to why all of the rules of algebra are what they are. You will be provided rigorous justification as to why the rules are the way they are and why the mathematics is the way that it is. Okay? All right. Checking real quick to see if there's anybody I need to let in. So far, no. Okay. Okay. Aha. There we go. Very nice. All right. Without further ado, let's start talking about 1.1. Basically, this section is all about numbers. We have all kinds of numbers at our disposal in mathematics, okay? Matter of fact, mathematics is all about numbers. Many people think mathematicians like me, all we do is like calculate big numbers in our head, and that's actually not the case. Mathematics is not about mental arithmetic. It is about deep connections formed between numbers. And that's not just arithmetic, that's not just adding, that's not just dividing, that's not just subtracting, that's not just multiplying. I'm gonna admit another individual here. Okay, it's not just those concepts, and you'll see what I mean by that as the course progresses. But human beings, the way that we are able to quantify reality is through the concept of numbers. So you ask, how many pieces of chalk do I have? I have 1, 2, 3, 4. Those are the first numbers we ever invented as human beings. They're called the counting numbers. And so naturally, we call them the natural numbers. This is the symbolic representation for the natural numbers. Okay, and they start off as 0, 1, 2, 3. You go on forever. Then we have the integers. Okay, the integers are very much like the natural numbers, except they include the negative numbers. And you go on to infinity, okay? So 100 is here, 102 is here, 103 is here, negative 1,740 is here. Okay? Then we talk about the rational numbers. This is a symbolic representation. This is rational. And the rational numbers are the fractions. So a rational number is any number that takes, for A and B integers, it takes a ratio of the two integers. So A and B is any integer. So, for example, 1/2 is a rational number. 3/4 is a rational number. 17 divided by 31 is a rational number, okay? So every time you take a ratio, in the numerator you put an integer, in the denominator you put an integer, you get a rational number, okay? And now, the number system that contains all of these numbers inside of it, the biggest number system that we will be talking about in this class, mainly, is the real numbers, denoted by this script R, real numbers. We like to keep it real in this course because we will also be talking about imaginary numbers down the line. We like to keep it real in this course, but we will also talk about imaginary numbers. Real numbers are numbers such as pi, okay? This is 3.14159 with like a infinite non-pattern containing sequence of values. Another real number is, let's say, 2.73645. Another real number is negative 13.2457346. You get my drift, right? So if I were to create a line out of the real numbers, here's 0, -1, -2, 1, 2. A real number can be an integer, of course. It can be a rational, of course. It can be a natural number, of course, but it also contains everything in between. So anything that falls in the real line is a real number. Okay, let me just take a look at the chat here to see if there's any questions so far. People are emailing to asking to be let in. Okay, there was one more individual. Yeah, it was Molly. Molly needed to get let in, and now Molly's in. Okay, nice to see you, Molly. Right now, we're talking about section 1.1. If there's anybody else showing up, we will continue to let them know. Everybody, if you have a question, make sure to ask it in the chat. It would be way too difficult to kind of have your audio on and even your video. I have removed your videos. So the only way I can interact with you right now is through the chat room. I don't see you, and I don't hear you, unfortunately. So the only way I can interact with you is the chat room. So what you guys need to do is, if you have questions when I'm going through the material, ask in the chat room. And also you can ask via email after the class is over. So it's up to you how you want to go about it. Now that we've described numbers, let's start playing with how do we combine numbers together. Mathematics is truly all about numbers and the secret patterns that are within them. That's what math is all about, numbers and the secret patterns within them. Board is not very clear to see. Oh, you marked that privately, and I just said it out loud. My bad. That's okay though. Don't worry about it. Is I'll try and wipe the thing with the tissue. Maybe there's some chalk on it. Hopefully that helps. Yeah, that kind of looks like it makes it better. Hopefully that helps. Is there a way to see the board better? Okay, hopefully that helps. I think it's too far also. We can fix that. How about I scoot it in for you a little bit? I will just adjust my calibration here. So I'm here. I'll adjust the calibration to here. All right, that's as good as I can do, guys. Is that better? I think it's too far. Thanks. You're very welcome. Is that better? Okay, wonderful. I see a lot of positive responses to that. Thanks, good for me. Okay, yeah, that's as close as I can get it realistically. Okay. All right, let me see if there's anybody who needs in. Nope, not so far. I see a hand emoji. Okay, so apparently we got emojis here. I can't sense your emotions, but sometimes I randomly see your emojis. Don't go crazy with that, okay? Don't be annoying with that. I'm just gonna ignore it. If you just got spam emojis, don't do that. All right. All right. Now let's talk about the order of operations. I know you heard this all the time, and you always thought it was some silly thing, like some preschool thing you had to remember. Please excuse my dear Aunt Sally. Please excuse my dear Aunt Sally. You always get told that that's the way that you memorize the order of operations, but you don't get told why that is the order of operations. Okay? This sequence is necessary to keep mathematics logically sound. Meaning, if we don't adhere to this sequence right here, then randomly in our equations, even though we didn't do anything wrong, we just violated the order of operations, we will get logical flaws. We will get something weird like 3 is equal to 17. And that is not true. 3 doesn't equal 17. So that's why we adhere to the order of operations, because if we didn't do so, it would mess the mathematics up. Furthermore, you have to have some type of order of operations that everybody follows, because if people have their own order of operations, then the output of the numbers won't align, even though you're doing the same thing. So we need to have a common way of doing the operations that not only adheres to the logic, but also is some type of standard that we all can follow. Okay, so P is parentheses this thing. E is exponent. They're really the powers, x to the p, powers. M is multiplication. D is division. is addition. And S is subtraction. Okay? Here's an example. How about we have 3 multiplied times 2 quantity squared minus 4 times the quantity 6 plus 2. Okay. Let's first follow the order of operations and see what we get. And then let's disobey. I had to let some people in, okay? I let some new people into the course. Welcome. Okay. First, we will follow the order of operations, and then we will not follow the order of operations. You're going to see that it matters. If you don't follow the order, you won't get the same answer as before. So we'll follow the order of operations. Parentheses first, meaning we look at the parentheses. Anything that's going on in the parentheses, that's what we attack first. So I look here and I see 3 times 2. I'm going to do that in these parentheses. And I see this 6 plus 2, so I'm going to do that in these parentheses. 6 plus 2 is obviously 8. 3 times 2 is obviously 6. That's it. We're adhering to, please excuse my dear Aunt Sally. Then there's exponents, E, which I told you is powers. So in order to obey, I'm a rebellious person, and I don't really like to obey anything. But the only reason I would obey something is because it makes logical sense. So sadly, I'm telling you to obey this, and it's actually not that bad. It's not that bad to obey something that is worth your while to obey. So next we talk about exponents, which are the same thing as powers, which are these numbers up here in this corner. This means square the 6. This means 6 times 6. And 6 times 6 is 36. Minus a 4 times our 8 here. So please excuse exponents. My multiplication. Okay, so where is the multiplication in here? Aha, there it is. So then we do that. So this becomes 36 minus 4 times 8 is 32, right? Okay, so now we did multiplication. Next comes division, which there isn't any. There's nothing to divide. Then becomes addition, which there isn't any. There's nothing to add. Then comes subtraction, which is the last step we need to do here. Okay, so we subtract, and our final answer becomes a 4. All right. Now let us disobey the order of operations, okay? Let us, letting some more people in here, okay? Letting some more individuals into the class, okay? So now, let us disobey the order of operations, okay? I'm going to let another individual in, okay? So let's not follow, please excuse my dear Aunt Sally. Let's go do what we want, all right? Let's do what we want first. So how could I mess this up? Well, I could square these first, all right? Notice that that would give me 3 squared times 2 squared, which that's really 9 times 4, which that's really 36. This is probably an example that still leads to the same answer. So I will have to construct a different example. Let me construct a different example here. Let's do 3 times 2 squared plus 5 divided by 13 minus 2 squared plus 3. Okay. Here, adhering to the order of operations, we get, this is a 6, squared plus 5 divided by, this is a 11 quantity squared plus 3. Notice that this gives us 36 plus 5 all over 121 plus 3, okay? Notice that 36 plus 5 is 41 all over 121 plus 3, okay? Then notice that if we were to not give a common denominator here, because this is divided by 1, if we were to just add 3 and not give a common denominator, gonna allow another individual here, then we would get some weird thing where it's over. This is it. But adhering to the order of operations gets us there. If we were to not adhere to the order of operations, and we were to try and add 3 first, the answer would not be sustainable. It wouldn't be correct. It wouldn't, oh, more individuals here. Okay. So you could try this in a calculator. You'll realize that if you don't put parentheses on division, that you won't get the right answer that, let's say, the computer is looking for, and you won't get the right answer that, let's say, your online interface is looking for. That's usually because you must have messed up the order of operations. Okay. Now we will talk about the product rule. Go here. Let some more people in. Look this up here. Go to modules. Okay. All right. What rule did you say? Please excuse my dear Aunt Sally. Oh, the product rule. Yes, that rule. Yeah, I'm constantly letting people in here. So, yes, that was the product rule. Of exponents. Okay, so let's say you have x to the m, some power, or let's say x to the p. Let's say you have some x to the p raised to some power, multiplied some x to the m, another power. Whenever you have numbers of the same base being multiplied times each other with different exponents, their exponents will add. This is where I will be different than any teacher that you've ever had. Usually teachers leave it at that, but no. Oh, you can't see what I wrote up there. It says product rule of exponents. It's all in your textbook. It's all in your textbook. I'm still in section 1.1. So what I wrote up there was and that means I need to calibrate this like that. Because above that line you can't see, huh? I can't see what you're up to. Awesome, thank you so much. No problem. No problem at all. For those of you who are new, who just walked into class, my only way of interacting with you is through the chat. So if you have any questions, let me know. So let me prove this to you. This is why I'm going to be different than any teacher that you've ever had before. I'm going to prove to you why this is the case. All right? For instance, let's take x squared times x cubed. Okay? What should we get when we have something like this? Well, this rule says that you should get x to the 2 plus 3, right? Which results in an x to the 5th. All right, but why is the rule true? Why is the rule giving us that? Well, take a look. What if I were to break apart this x squared? That's just really x times x. Is it not? Only if the exponents are the same, you can add. Only if the base is the same. The base. This x right here is called the base. Only when the base are the same, you add the exponents. Very good question. This x right here is called the base. It's the number that's being raised to the power, okay? So breaking apart this, I'm going to justify why this becomes x to the 5th. I'm going to justify it without this rule to show you that this rule is because of the justification. X squared is really x times itself. And guess what x cubed will be? X times itself 3 times. You guys see that? Now, look, how many x's do you see? When I count the number of x's, how many x's do I find? Someone type it in for me. How many x's are up there? 5. Yes, that's right. Yes, it's 5. That's why we say x to the 5th. Make sense? Yeah, I see a lot of 5s. Wow, okay, good. You guys clearly can count. That means if you could count, you could do math. Seriously. 5, yep, very good. Yep. So look, that's why that's the case. Let's do another example. Let's do y to the 13th times y to the 12th. What do we get here? Well, actually, you know what? I'm going to change this because I still want to bark up the same alley. I'm going to say y to the 4th times y to the 5th because I just want to bark up the same alley for now, okay? Y to the 25th, y to the 9th. Yeah, I know you want that, but I'm not going to do that yet. Oh, it's because, yeah, I changed that. I changed it. So now it's y to the 4th times y to the 5th. Because they have the same base, okay, we can use the product rule for exponents, meaning this should be y to the 4th plus 5, and that's y to the 9th. Okay, that's why you guys are saying y to the 9th. Very good, very good, very good. Okay, but again, why is this overarching rule true? It's because of this phenomenon right here. How many y's times each other is y to the 4th? It's 4 of them. Y times y times y times y. And then how many y's is y to the 5th? It's y times itself 5 times. Count how many y's we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of them, correct? So how come you would multiply them together since they're in parentheses? Good question. The parentheses is just covering them, and you're multiplying them secretly. I could have put a dot here, but I neglected to do so because it is a standard mathematical practice that if you ever put 2 things next to each other, like x, y, like that, this really means x multiplied times y. So they're the same thing. It's just shorthand. Does that answer your question? Janice? He is breaking it down, the exponent, to show you a visual. You will not continue the problem. Yeah, I'm trying to read some of the stuff you guys are saying. Oh, okay, I see you, I see you. Very good. I don't see you, but I'm glad you see me, if that makes sense. Yes, that's exactly why this exponent rule is true to begin with. It's because when you break it down, this always happens. So mathematicians decided to generalize it and make the powers anything, as long as the base is the same. So let's stop using x's and y's and start using real numbers. And if you don't record something I wrote and I deleted it, don't worry. This is getting recorded and re-uploaded. So you will be able to rewatch this video over and over and over again. So if I erase something prior to you writing it down, do not worry about it. Just sit back and relax and think. Think of any questions you have, okay? Let me check to see if any people coming in. Nope, okay. So how about 3 squared times 3 to the 7th? Now the base is 3. It's not x, it's not y, it's 3. So when you have the same base, the exponents, and you multiply the two numbers, when you have the same base, the exponents add. This becomes 3 to the 2 plus 7. Whenever you have the same base and you're multiplying them, their exponents add. Is that the same for all lectures? Yes, that is the same for all lectures. So our end result is 3 to the 9th. Okay, and I could just do the 3, see 3 times 3, 3, 3, 3, 3, 3, 3, 3, 1, 2, 3, 4, 5, 6, 7. How many 3s you got? You got 9 3s, right? And they're all times each other. Somebody went through and put it in the calculator. 19683. Thank you for that. But I'll have you know, as a mathematician, we're happy with that. We don't need you to plug it in. But I appreciate your efforts and your desire to contribute. Thank you so much. Yes, thank you so much. But yeah, this would be sufficient for me. I'm not the computer input. So whenever you're doing your homework, the computer input will dictate how it wants the final answer. If it says have it as just a power, expressed as a power, then do it like this. If it says what is the numerical value once you compute it, then actually your answer, Hanita, is what it would be looking for. So what is the right answer depends on what is the question. If the question is asking you to put it in like this, then put it in like that. If it's asking you to do the 3 to the 9th, actually compute what number that provides you, then your answer would be the right answer. Why wouldn't you multiply the whole numbers, the 3, along with adding the exponents? That's a very good question. Notice that in each of the 3's, the exponent is 1. 1, 1, 1, 1, 1, 1, 1, 1, 1. So this really reduces to 3 to the 1 plus 1 plus 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice that this reduces to 3 to the 9th. Does that answer your question, Sonia? Over here, this is 3 to the 1st power. 3 to the 1st power. So whenever you have the same base, the exponents add, just like we're doing here. So you just add 9 ones, which 1 plus 1 9 times is 9. Yes, thank you. Thank you. It's not going to be 9 raised to the 9 because our base was always 3. That's why. Okay. Now we're going to talk about the quotient rule of exponents. This is very similar to the product rule, except quotient implores us to talk about division, not multiplication. It says that x raised to the power p divided by x raised to the power m will equal x to the p minus m, where x to the m does not equal 0. Because we can't divide by 0. I know you're all asking. I know you're all in there in your houses or wherever you're at. I know you're asking. I've heard that so many times, but nobody has told me why you can't divide by 0. Besides, that's just the rules. Don't ask why. Someone put it in the chat if you agree with that. And if you don't agree, say, no, I don't agree. So I want people in the chat to be like, I agree, or don't agree. And I won't be upset at you if you say if you agree or not. I just want to know. It's kind of like a poll. Oh, wow, I see a lot of people agreeing. Oh, my goodness. It's as if I've been a student before in your position and I was, yeah. Makes sense to me. Well, we need to, as mathematicians, we're all going to be mathematicians together. We as mathematicians have to justify why we can't do something. We can't just say, don't do it because I said so. That doesn't work in mathematics. Nobody has the authority to say, don't do it because I said so. You do have the authority to say, don't do it because of all of this justification. And I'll show you the justification. Here's why you can't divide by 0, something that you have never been told. Okay. Let's get any number, okay? Any number. Let's say 3. We've been using 3 a lot. Let's divide it by 0. Let's do something they say that is not allowed. Let us assume it's allowed, okay? Assume that it is allowed to divide by 0. What would it equal? Someone's saying 3. Okay, let's say it equals 3. Let's say it is allowed and it equals 3. Well, let me multiply both sides by 0 then to solve. Multiply both sides times 0. Cancel, cancel. So I get 3 is equal to 3 times 0, right? Because when I multiply both sides by 0, the 0 cancels out in the denominator here, and then it gets multiplied times the 3 right here. Well, multiplying 0 is 0, so maybe division is 0 as well. I'll show you what's going wrong here, Isaac. I'll show you what's going wrong here. Notice that 3 is equal to 3 times 0 now, but what is 0 times any number? Someone write it. 0 times any number equals 0, 0, 0. I want to see a lot of zeros. Everybody type in a 0 for me. 0, 0, 0, 0, 0. But notice this implies that 3 is equal to 0. Notice that that implies 3 is equivalent to the number 0. Is that true? No, 3 doesn't equal 0. This is a contradiction. So we don't divide by 0 because it causes mathematical contradictions. We don't divide by 0 because some lame teacher who's probably awesome because they don't get paid enough and they hate their lives tells you to do so. This is a pitch to all individuals. I mean, most people in society know teachers should get paid more, but I'm going to pitch that out from there again. Okay? That's why you can't divide by 0. But you know what? I'm not even satisfied by that, because I've had some very clever students say, well, what about 0 divided by 0? Isn't that equal like 1? You'd think so though, right? Shouldn't 0 divided by 0 equal 1? I mean, 3 divided by 3 is 1. 2 divided by 2 is 1. 17 divided by 17 is 1. Why shouldn't 0 divided by 0 be 1? Don't you guys agree that maybe this should be true? Can I get some yays and some nays? Agreed, yeah, it should be true. Yes, it should. It should. A lot of people think, yeah, it should. If you divide any number by itself and it always equals 1, then why is 0 an exception to that rule, right? Yeah, you all agree that it should equal 1, but it doesn't. And I'll show you why. multiply both sides times 0. So I get 0 is equal to 1 times 0. But I mean, hey, that's just equal to 0. 0 equals 0. There's no contradictions here. You are lying, Professor Niazi. We found you. All mathematics is wrong. We found a contradiction in all of mathematics, and all the Zermelo-Fraenkel axioms are incorrect. Not so fast. You can't split 0 pizza into 0 slices and get a slice. That's technically true. Yeah. Okay. Here's what we're going to do here. Let's restore this equation. Okay. 0 is equal to 1 times 0. Now, let's add a 1 times 0 to both sides. Really, we're just adding a 0 to both sides, so it doesn't matter, right? 0 plus 0 is 0, which is equal to 0. Which is equal to 0 plus 0 is equal to 0, which is equal to 1 times 0 plus 1 times 0, which is equal to 0 plus 0, which is equal to 0. Okay, notice that over here on this side, we can factor out a 0. This becomes 1. So on both sides, we can factor out a 1 here. I can factor out a 1 here. So I get 0 plus 0 over here. Okay. And over here, I can factor out a 0. So I get 1 plus what? Notice that if I were to factor out a 0 from here, this would be a 1, but I could place any number here if I wanted to. I could put in a 100 here, I could put it in a 5,000 here, I can put a 4 billion in here, because once I set that 0 back in there, it'll multiply to be 0. So let's just say that this is some number n. Any number can fit in there, and then everything will be okay, right? Right? So now, dividing by 0, we'll move over here. We'll get 1 plus n is equal to 1 times 0 plus 0 divided by 0, where n is any number possible. And this should be an equation that holds. But notice that then I get 1 plus n is equal to 1 times 0 plus 0 is just 1 times 0 all over 0. And then I get 1 plus n is 1 times 0 over 0, which is 0 over 0. Okay. But by hypothesis, by our assumption, 0 over 0 was 1. Our fundamental assumption when we began this problem was 0 over 0 is equal to 1. So that means 1 plus n is equal to 1. Contradiction. 1 plus n equaling to 1. That's a contradiction, because n could have been any number, remember? If I pick n to be 7, that would mean 1 plus 7 is equal to 1. Is this true? No. 1 plus 7 is 8. 8 does not equal 1. Contradiction. This is a symbol mathematicians use to say contradiction. I see a lot of yeah. Yeah, that's right. This is precisely why you can't divide by 0, ever. And this is precisely why 0 over 0 doesn't even equal 1, because it results in mathematical contradictions. Nobody be scared right now, okay? I'm going to let somebody else in. I know some of you guys are wondering, oh my gosh, is this going to be on the test? No. None of this, what I just showed you right now about dividing by 0, will be on your test. None of it will be on your test. This is just here for your information. And you are perfectly capable of understanding it. That's why I provide it to you, because I know every single one of you are perfectly capable to understanding it. Because you can add 1 plus 7, you get that that equals 8. I'm going to erase, even though you can rewatch it, and you can rewatch the recording over and over again. So that's just for you guys to get your curiosity satisfied about something that you've most likely been wondering every single day of your lives. The quotient rule of exponents, remember, was x to the p divided by x to the m is equal to x to the p minus m, where x to the m can't equal 0. And now we know why. You can't divide by 0, and now we know why you can't. So that's what's so great. Applying this to a situation like x cubed divided by x squared, most people will see that and think, I don't need any rules for this. Clearly, that's just x. But using the quotient rule, notice that this gives us x to the power 3 minus 2, which is the same thing as x to the power 1, which is just x. It's exactly what you intuitively thought. And breaking it down even further, notice that the numerator is a product of 3 x's, and the denominator is a product of 2 x's. And so through standard cancellation, cancel 1, cancel 1, cancel 2, cancel 2. All that I'm remaining is with the x on top, with a 1 on the bottom. And x divided by 1 is just x. Okay? So that's why that happens the way it does. Let's do another example. How about y to the 14 divided by y to the third? How do we simplify that? Well, we use the quotient rule of exponents. You say this is y to the 14 minus 3. Okay? The power. It's in the power. That's in the exponent. So then this just becomes y to the 11. And I could have broken it down just like this, but that's drawing a lot of y's. Okay? Now, let me define what a negative power is. And yes, there is such a thing as a negative power. Negative exponents. Well, let's say I have x to the negative p. I have some x. I have some number. It's raised to the negative power p. P can be a number, 5, 6, 7. Let's say it's raised to the negative p. This is equivalent to 1 over x raised to the p. That's just what it's defined to be. Don't ask questions why. Knowing me now, does that sound like something I'll ever accept? No, 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 not at all. Right. I wouldn't accept that, and neither should you. So I will show you why we define negative exponents the way that they are. It all comes down to x raised to the 0 power. Who here can tell me what any number raised to the 0th power is that you've been forced to regurgitate? Anything raised to the 0th power is equal to what? 1. Some people say 0, but no, it's 1, I believe. Yeah, 1. You've been force-fed. Some of you maybe don't remember. Some of you erased it from your brain because you also are rebellious like me. You don't want to listen to other people. Yeah, 1. I get in a lot of 1s. Yes. You have been forced into submission, into believing that, yes, any number raised to the 0th power is equal to 1. You've been forced to do it. Well, it's a good thing you were forced to do something that is true, but it's not a good thing that you weren't given justification as to why that's the case. Let me repeat that. It's a good thing you were forced to do something that is true, but it's not a good thing that you were forced to do it without giving justification as to why it is true. Matter of fact, if you are not given justification to do something and you're forced to do it, then it's just as bad as being forced to do something that is false, because you as an individual are not able to determine whether what you're doing is true or not, or good or not, or bad or not. So you're being led astray. You're being led, and you're just depending on the people who are teaching you this stuff. You're depending on them being right. And that's never been my style. And that should never be your style either. Okay? I'm going to prove to you why any number raised to the 0th power is equal to 1 right now. And it involves this definition. So notice that x to the 0 is really the same thing as x raised to some power minus that power. Because p minus p is 0, right? 3 minus 3 is 0. 5 minus 5 is 0. 7 minus 7 is 0. So I can hop back to this side of the fence because of that fact. But notice that this is the same thing as x to the p times x to the negative p. Doing the reverse of the product rule. Remember the product rule? Where we said the exponents add? Now we're undoing the product rule. Notice that by this definition, if it holds true, this means x to the p is all over x to the p. This x to the negative p reduces to 1 over x to the p. So it ends up flipping down into the denominator. Notice that anything divided by itself, as long as it's not 0 divided by itself, is equal to 1. This is why any number raised to the 0th power is equal to 1. And this works with any number. I'm using x, which might seem confusing, but I could use any number. 3 to the 0. 3 to the 0, or yeah, 3 to the 0. That's the same thing as 3 to the 12 minus 12. Matter of fact, that's the same thing as 3 raised to the 7 minus 7. Every time you subtract something from itself, you get 0, right? Yes. And so this then would result in 3 to the 7th divided by 3 to the 7th. And anything divided by itself is 1. It could also be 3 to the 12th divided by 3 to the 12th. Anything divided by itself is 1. So notice that we discovered this as mathematicians like this. We didn't know what 3 to the 0th was. We knew 3 to the 1st power as itself. We knew 3 squared was, let's say, 9. And then we said, well, what should 3 to the negative 1 be, logically? Well, they guessed it should be this. And 3 to the negative 2 should be 1 over 9. Because this is 1 over 3 to the 1. And this is 1 over 3 to the negative 2. Or positive 2. 1 over 3 to the positive 2. So they noticed that, hey, look what's going on here in this pattern. 9, 3, unknown, 1/3, 1/9. So this convention has been adopted to understand what any number raised to the 0th power will be. And it must equal 1. Very good. You guys enjoying class so far? Let me see what the chat say. Oh, wow, a lot of yeses. I'm so surprised. So now we have a power rule of exponents. Before we had a product rule of exponents. Now we have a power rule of exponents. Power. So here's the rule. X raised to the m raised to the p power. What would that be? Some teachers don't explain, they say watch Khan Academy. That is a sorry thing to say. Anyways, the power rule of exponents gives us that this is equal to x to the m times the p. Justification, loading. Here's a simple example. How about I have x squared raised to the 4th power? Let's say we don't even know the power rule of exponents. Let's try and discover what that equals, okay? Notice that x squared is x times itself, twice. Raise that to the 4th power. Well, x times x raised to the 4th power means x times itself 4 times. So then that equals x times x, x times x, x times x, x times x. X times x raised to the 4th power is x times x times itself 4 times. So notice we write that all out. And how many x's do you guys count? Someone says 8. Let me double check you. 1, 2, 3, 4, 5, 6, 7, 8. Okay, yeah. That means when we have a bunch of x's raised to the 1st power, that they add up to x to the 8. Notice that we could have gotten that right off the bat if we said that this was x to the 2 times 4, which is x to the 8. Yeah, I see a lot of 8s. Very good. Oh, here's a math joke. Why is 7 scared of 6? Why is 7 scared of 6? Seven is scared of 6. This is a reference for Halloween, you know, Halloween coming up, and it's all about that scary stuff. It's because 7, 8, 9. Yeah, someone knows the joke. Yeah, very good, Sonia. You know the joke. Round of applause for Sonia. She knew the joke. Yeah, this is the power rule for exponents. So this applies for any weird situations. So what is 3 squared raised to the 14th power? I don't got to do this business anymore. We found the general way of doing it in all cases. So I don't have to justify it anymore. Once I've justified it once, I don't need to do it over and over again. Once I found the general rule, I know that, oh, that will just be 2 times 14 in the power, which that means that's 3 to the 28th power. That's a huge number. Professor Niazi, does that work for negative exponents? Yes, it does. X to the negative 3 to the 4th power. What would that give us? Do you mean y is 6 scared 7? Probably. I probably messed the joke up. My bad. Maybe I messed the joke up. It's something like that. It's just 7, 8, 9. Oh, wait. 6, 8, 9. Or no, yeah, 7, 8, 9. Yeah, that's right. 7, 8, 9. Yeah. So 8 is scared of 7? I don't know. Something like that. Someone was scared because 8, 9. It sounds like you're eating stuff. Okay? So notice that this will equal x to the negative 3 times 4. So now that means I get x to the negative 12. Which x to the negative 12, as we've discovered, is really 1 over x to the positive 12. Every time you see a negative exponent, you put a 1, divide by the positive exponent. So 12 to the negative 5 is just 1 over 12 to the positive 5. 3 to the negative 3 is the same thing as 1 over 3 to the positive 3. Y to the negative 144 is the same thing as 1 over y to the positive 144. Just remember that and you'll be okay. Now, one last thing though. I'm going to throw you a curve ball. What about 1 over x to the negative 3. What is that? Well, it's actually not that hard. You just apply the same rule. Well, if it's x to the negative 3, well, then that's 1 over x to the positive 3. But notice we have this 1 over 3 business. How do we fix that? Well, we multiply by reciprocals. Notice that the top is 1, but 1 is the same thing as 1 over 1, because 1 divided by 1 is 1. And that means I can multiply the top and bottom by a fancy number 1. This is called multiplication by reciprocals, because you get this number, you flip it, and you multiply top and bottom by that value. And it's really a fancy number 1, because x cubed divided by 1 divided by x cubed divided by 1 is really 1. Multiplying anything times 1 doesn't change the number, so we can get away with it. And in doing so, not only do we get away with it, but the denominator cancels, and we attain a new numerator. You get x cubed divided by 1, which is just, you don't got to do that. We can just say it's just x cubed. So notice, if the negative is in the denominator, it just takes it into the numerator. If the negative is in the numerator, it takes it into the denominator. Is the square root thing? Maybe. Maybe. Square roots will be coming up. Cube roots will be coming up too. All kinds of roots will be coming up. Pull them roots up. It's farming season. All right. Here's an exponent rule. X over y raised to some power p. What does that equal? Well, the power actually distributes to numerator and denominator. Example, 2 over 3 raised to the 4th power. That would be 2 to the 4th divided by 3 to the 4th. Proving such a thing is as easy as just multiplying them out all over again like we've been doing. Okay. And so this is a rule. Here's another rule. X times y raised to some power with the quantity around it. That equals x to the p times y to the p. The power travels across both in the product. For example, 2 times 3 squared is the same thing as 2 squared times 3 squared. Here's the proof. It doesn't matter. So here I can go down this way and say this is 6 squared, which is 36. Or I can go this way and say this is 4 times 9, which is also 36. Agree. Very good. The corny jokes are the best part of this. Oh, ha 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 ha. Square root thing. Agree. I'm glad people are following and enjoying. That's good. All right. Let me erase this right here. Okay, so one thing I will note, here's a pitfall. Here's a pitfall. A lot of students will fall and they'll make errors in their calculations here. X plus y quantity raised to some power p. Does this equal, I'll put a question mark here, x to the p plus y to the p? Question mark? No! Here's why. Here's an example. Let's do 2 plus 3 raised to the 2nd power and compare it to 2 squared plus 3 squared. Are these equivalent? Here's where order of operations clearly matters, you guys, you see. So when we add them first, I get this is 5 squared, which equals 25. But when we let the squares travel, this becomes 4 plus 9, which is 13. Class, does 13 equal 25? No, 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 no. I see a lot of no's. That's good. No, it doesn't. So this is, you can't do it. So now that I've warned you, do not do this. Do not do this. Also, do not do this version. Do not do this other pitfall, x minus y to the p. It, in fact, does not equal x to the p minus y to the p. It won't. So powers travel across multiplication and division, but they do not travel across addition and subtraction. So do not make that error. And if you're ever wondering, just plug some numbers and check. Look, again, like with 2 minus 3 squared versus 2 squared minus 3 squared. Notice this, I get a negative 1 squared, which is 1. And don't get me started on why a negative times a negative is a positive. I'm going to wait until next class to do that because we're a little behind on schedule because of the technology issues and some of that stuff. So I got to give you something to be excited about, right? So next class period, I will prove to you why negative times a negative is a positive. All right. But so far, I hate saying this, but accept it for now. I guarantee you, you will get the proof later. Looking forward to that. Yes, it's very interesting. It is very interesting. It's all just a consequence of logic. But yeah, this equals 1. This equals 4 minus a 9. But that's negative what? 4, 5, 6, 7, 8, 9. That's a negative 5. Class, does 1 equal negative 5? No. So that's why we can't allow this rule, because it leads to logical, incorrect logic. It leads to results like 1 is equal to negative 5. And you don't want your mathematics doing that. You don't want your mathematics doing that. It will be terrible. If you build a bridge off of mathematics like this, the bridge will fall. It will crumble. Let's do some examples here. How about, this is a good one. How about negative x raised to the 5th? And now I want to raise this whole thing to the 2nd power. Okay? Order of operations says parentheses. But there's 2 parentheses, right? Well, you got to do the first parentheses, and that's the innermost parentheses. That says take a negative x and take it to the 5th power. Any negative number raised to an odd power results in a negative number. Need I explain why? I will explain it. Negative x quantity to the 5th power is negative x quantity times itself 5 times. 1, 2, 3, 4, 5. Notice that a negative times a negative is a positive, right? So these will become positive. These will become positive, but then the negative remains. So it ends up becoming a negative x to the 5th. And so this will actually always happen with any odd power. If you take a negative number, raise it to an odd power, because there's that one guy remaining, these will pair up, and then there'll be that one guy remaining making the overall thing negative. Whereas if I were to say negative x to the 4th power, that's this. Notice that when you pair them, they become positive. Pair them, they become positive. So your overall result was x to the positive 4th, positive x to the 4th. So raising a negative number to an even power always makes the negative go away. and raising a negative number to an odd power retains the negative. Yeah, the double parentheses, don't be scared about it. What you got to do when you see double parentheses is focus on the innermost parenthesis, address it like we just did, and then it goes away after you address it. So now there's only one parenthesis remaining. And then once we square this, this is just really, remember, an odd value raised to an even power makes a negative value raised to an even power makes the negative goes away. So then this becomes x to the 5 times 2, x to the 10th, which you could have seen that by saying this is this. Negative times a negative is a positive. I will prove it to you. I will prove to you next class. It'll give you something to look forward to. Negative times a negative is a positive. There is justification for it, but you know, we're a little behind, and I gotta leave you fiending for some more later, some more math for next week. Now let's talk about scientific notation. Okay, scientific notation allows us to express very large or very small numbers in a very compact way. For instance, a million, 1 million, a million. That's what that is, a million. 1 million is that number. But in scientific notation, this is 1.0 times 10 to the power of 6. How did you come up with that, Professor Niazi? Well, all you got to do I'm not changing anything. I'm just creating some space here. I didn't change anything. I just scooted the numbers back a little bit. Notice that at the end of the 1 million, I can put a decimal and a 0 right here. Okay? So there's secretly a decimal there. All right? Here's how you do scientific notation. You get the decimal, and if you go left, you increase the powers of this 10 by each increment. 1, 2, 3, 4, 5, 6. And what remains, you put 1.0 times 10 to the 6. So guess what a billion would be? This is a billion. 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Okay, so at the end we can put a .0. What does this equal in scientific notation? Can someone tell me? Well, we play the game again. Every time we go left, this 10 to the power increases by 1. So this is going to be 1.0 times 10 to some power. We just don't know it yet. We have to count how many times. Aha! 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 Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I put 1.0 times 10 to the 9. So you got to remember, if you're counting towards the left, it's going to be increasing the numbers up here by 1 each time. Now, let's go in reverse. Let's do a really small number. 0.00000002. How can I express this really small number in scientific notation? Well, it's going to equal 2.0 times 10 to some power. And now we're going to count to the right. 1, 2, 3, 4, 5, 6, 7. So this becomes 2.0 times 10 to the negative 7th power. So when you go from left to right, each time you go count and then put a negative on it. And then when you go from right to left, each time count and put that number up there in a positive value. It's okay, Joe. It's all right. You cannot learn if you don't make mistakes. It is impossible to learn something without making mistakes. If you want to get good at something, make as many mistakes in that thing as possible. Like riding a bike. If you want to get good at riding a bike, try riding the bike down the steepest slope like Mount Everest. No, don't do that. But you get what I mean. If you survive that, you would learn from that mistake that, hey, maybe I shouldn't be riding my bike down Mount Everest. But what I mean to say is, when you were learning how to ride a bike, you definitely fell. You fell a lot. But in doing so, you learned stability and how to flex your core and to keep yourself like on the bike to the point where you eventually learned. So mistakes are part of learning. Why you go behind the two? Well, because that's how scientific notation likes it to be. That's a good question. I could have said that this is 0.20 times 10 to some power. I could have stopped just short here, right? So then it would be 0.20 times 10 to the negative 6. These are the same. 2.0 times 10 to the negative 7 and 0.20 times 10 to the negative 6 are the same thing. It's just one of them is more desirable when we do scientific notation. We tend to want it like this. Okay, that's why. Oh, okay, thank you. You are very welcome. Very welcome. Now that we've mastered scientific notation, let us go one step further beyond. Now it's like divide them and stuff. 2.0 times 10 to the 13th power. What is this? Divided by 4.0 times 10, let's say to the 17th power. What does this equal? Holy crap, that looks hard, right? No, it's not hard. It's not hard at all. You are very well equipped to answer these questions. You know scientific notation, and you know the exponent rules. So you're very well equipped to do this. The way you do this is get this number out here, divide them. Then put a 10 times, or a times 10 raised to, use the quotient rule. Remember the quotient rule? You get the numerator power subtracted by the denominator power. And that's that. 2 divided by 4 is just 1/2, or in decimal notation, 0.5. And 13 minus 17 is negative 4. Okay, so this begs the question to who asked that? Janice. Why can't we just leave it like this? We totally could, but we want to make it look like this in our practice in scientific notation because it's just more preferable. I'll tell you the real reason. In science, we want to know what the decimals over here are. We don't really care what the decimals over there are. So we want to know more about what the decimals on the other side of the dot are. So in order to write this like this, I got the decimal and I scooted it just one place. I went from left to right. How does that alter the power? What does it make it? You can remember the rule of going left to right does this and going right to left does that. I mean, over here, look, when we count from right to left, the power goes up. And we go from left to right, the power goes down. Another way, just heuristic argument is you got 0.5 and made it 5.0. You got a smaller number and made it look bigger. You magnified it. So there's a cost. If you magnified its expression here, you have to minimize its expression here. So both ways of thinking work. This is just my intuitive way of thinking about it. Okay. Yes. So now let's apply scientific notation to an interesting and alarming problem. This problem is interesting and alarming. Okay. In 2014, the U.S. population was 308 million people. Okay. And the national debt was 17,547,000,000,000. So that's like 9 zeros after this number. It's a huge number. That's how much the national debt is. In 2014, can you imagine what it is now? That's highly alarming. It is a word problem. You will learn to like word problems. Matter of fact, I'm going to make you like all problems because problems require solutions, and formulating solutions is fun. It's like working out for your brain. So the question asks us, how much does each person owe? What is, on average, if we divided the debt evenly across all the population, what is the average debt of an individual in the United States of America? So it's useful to do this as a scientific notation problem, because remember, scientific notation is useful taking large numbers and making them compact, or very tiny numbers and making them compact. So this number right here, I can write 308 million as 3.08 times 10 to the, I don't know the power, but I can figure it out. 1, 2, 3, 4, 5, 6, 7, 8 people. And I can make this extremely egregiously large debt into scientific notation. It would be 1.7, let's say 1.75 times 10 raised to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13th power. 13th power. So this is the number of people in scientific notation. This is the number of debt in scientific notation. So what is the debt per person? Debt per person. Okay, we just divide these two numbers. If I want to know debt per person, then debt goes in the denominator and the person goes into the debt goes into the numerator, and then the person goes into the denominator. So the people go down here, 3.08 times 10 to the 8. And the numerator is 1.75 times 10 to the 13. So how you solve this problem? Remember, I showed you how to divide scientific notation. You get these numbers out in front and divide them, 1.75 divided by 3.08. Times 10 raised to the 13 minus 8. Okay? Once you get out your handy dandy calculators and you do this stuff and student loans. Yeah, I know. So yeah, once you get your handy dandy calculator and you compute this, you get 0.513 times 10 to the negative 13. And recall, us scientists kind of want this decimal over here. So we'll move it over one more time. So I get 5.13 times 10 raised to what power? You made something small more magnified, so the price you had to pay was decreased its power. So whoa, wait, there's an error here. This does not need to be negative 13. 13 minus 8 is 5. So this should be a 5. Okay. 13 minus 8 is 5. All right. So now in order to move this, I'm magnifying it. So I had to pay the price. It's still the same notion. It's 5.13 times 10 to the 4. And a matter of fact, it's not the only thing I messed up. I messed up these numbers here when I did the calculator stuff. This should be 0.568. And so when we do this, this becomes 5.68. Just some visual errors. But the answer remains that. So notice, if I want to no longer have this in scientific notation, and I just want to observe what is that number in the normal expression, that becomes 5. So I got to move this over 4 times. 1, 2, 3, 4. So this becomes 56800 point. And whenever you expand it in the calculator, it actually becomes the values that I haven't included are 56818.18 dollar per person. So that's nearly $57,000 on average of debt per person, which is incredible. That is very high. But sometimes debt can be a good thing if you get the debt in the right place, you know. Oh, I see a hand is up. I see a virtual hand. Janice has a virtual hand up. I don't know what to do about that. Do you have a question, Janice? Did you ask a question like a long time ago and I didn't see? Yo, it can't be that easy. What are you talking about? I raised it ages ago. You answered it. All right, there we go. Cool. Boom. And I just lowered your hand there. Okay. Cool. Okay. Now, I'm gonna have to do it like this. Boom, boom. Okay. I'm just rearranging some of these things. Okay, so here's the chat. Okay. I'm having some Zoom issues here. I just wanted to lower a hand, and now everything's going crazy here. So how about I minimize this? Okay, I'm gonna go back here. How do I open the chat up? Oh, click here. Boom. No, you didn't mess everything up. Don't worry about it. I'm just trying to get to know Zoom better. And here we go. I mean, it should be simple here. Okay, here's participants. I can have this up here. I can have this down here. And then I need to look up this right here. Okay, cool. Cool. So now, let's get to I'm going to look up your book real quick. Modules. Now we're moving on to 1.3. And since this is taking so long, I'm going to give everybody in class a 5-minute break so you can go use the restroom and stretch or whatnot. I typically do this on these long classes anyways in real life. Give people a time to go use the restroom or whatever. There we go. Boom. How do you access the book? It should be on Canvas. Go to Canvas and look at the modules. Go to Canvas on your left. It should say modules. And then click on that, and then it'll show you how to get to each section. So scroll through and find section 1.3. That's radicals and exponents. I'm lecturing out of the book. Hey, while you say that, how do I access the book? Yeah. You go to Canvas, you click modules, then you have options to click on the reading, and that'll give you access to the text. Okay. Let me know if you found it. That should get you there. So, okay. Did you find it? Did y'all find the textbook? Found it. Very good. Good to see that. All right. So that's around 5 minutes. So let's continue lecture. Again, I mean, really it's recorded. Oh, I know I need to erase that. Really it's recorded, so you'll be able to watch it later as well if I went over stuff that you didn't see. Okay, now we talk about square roots. Remember we talked about root, you were wondering about whether we're going to talk about square roots or not. Truth is yes. Okay, for A and B an element of the real numbers, meaning we have the real line. Here's 0. A and B can be found on the real line somewhere. Let's say A is here, let's say B is there. They're arbitrary numbers. It could be A could be 2, B could be 7, you know. For A and B, there are real numbers, okay? There's arbitrary real numbers, but once we do this, they will no longer be arbitrary. The square root of A is equal to some number B, and B has this property, such that B raised to the second power, or when you square B, it equals A. This is a very weird, but it's weird, but it's clear at the same time. Here's an example. Let A equal 9. This is going to mean B is going to equal 3. Because look, square root of 9 is equal to 3. And 3 is the number B. And B is the number such that when you square it, it gives you 9, which is A. So that's why that definition is the case. So we just defined the principal square root. This definition right here, it's called the principal square root. Okay. Now, this funny looking shape here, right here, that's called the radical. We typically call this the radical, okay? And I know what you're wondering, Professor Niazi, the square root of 9 is not 3, you liar. The square root of 9 is actually plus or minus 3, because not only does 3 squared restore the 9, but also negative 3 squared restores the 9. Why are you lying to us? I was starting to trust you. And now you're just out here lying, huh? Typical professor behavior. Not really. Actually, I'm not lying. Because the principal square root only takes the positive value. The square root gives positive and negative, okay? But the principal square root only gives you the positive value, okay? It can be negative and positive. I love radicals. I like to hear that. I like to hear that there's people that like radicals. Very good. Awesome. Okay. So now, when I take the square root, I better say plus or minus the answer. But if I say the principal square root, then I only care about the positive answer. Okay? Now that that's out of the way, what is the principal square root of 100? Okay? And before I even answer that, who here knows what the fundamental theorem of arithmetic is? Answer yes if you know, Or no if you don't know. Who here knows what the fundamental theorem of arithmetic is? No, 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 don't think so. Nah, no, nobody knows what the fundamental theorem of arithmetic is. A goodie. Sounds familiar. Okay. Well, I'll explain it to you. Somebody pick a number. Oh, wait. First, I have to explain what a prime number is. Okay. Who here knows what a prime number is? I do. Kinda. I do. I know what a prime number is. Some people know what a prime number is. I can't remember. I don't blame you. Okay. Here's what a prime number is. I am a number theorist, and we love prime numbers. Here's what a prime number is. Okay. A prime number is any number that is only divisible by itself or 1. So let me give you examples of prime numbers, and let me give you examples of not prime numbers. Prime number, let's say 3. 3 is prime because no other number can divide it besides 1 or 3. So 1 can go into 3 times, so it divided it. And 3 can go into 3 once, so it's prime. Here's an example of not prime. 4. Because although 4 can go into 4 once, and although 1 can go into 4 times, notice that I can find a different number that is not 4 that can go into it, namely 2. 2 can go into 4 twice. And so it makes it not prime. Let me give you another one. 7. The only numbers that can go into 7 evenly is 1 or 7 itself. 1 can go into 7 times, and 7 can go into itself once. So 7 is prime because of that fact. Let me give you a number that's not prime. 8. 8 is very not prime because, yes, 8 can go into 8 once, and 1 can go into 8 times. But take a look. 2 can go into 8 4 times. And 4 can go into 8 2 times. So it's definitely not prime. So odd numbers, prime is odd numbers. Good question. All prime numbers are odd, but not all odd numbers are prime. For example, 15. This is an odd number, but it is not prime because guess what can go into 15? 5 can go into 15 3 times. And, yeah. And 3 can go into 15 3, 6, 9, 12, 5 times. Yeah. So all prime numbers are odd except for 2. But not all odd numbers are prime. 2 is the only even prime number. Notice 2 is also prime. Only 1 can go into 2, and 2 can go into 2 evenly. Every other prime number is odd. So now that you know prime numbers, I can begin to explain to you the fundamental theorem of arithmetic. Somebody at home in your chat, and the first person who does this wins the contest. Give me a number between 1 and 100 that is not prime. Whoever gets it first, 24, okay. 24, 17 is prime. Looks like 24 wins. Here's the fundamental theorem of arithmetic. You're giving me a not prime number, 24. The fundamental theorem of arithmetic states that for any integer that is not prime, we can decompose it into a product of distinct prime numbers at various powers. It's really cool. Notice that 24 is the same thing as 2 times 12, is it not? But that is the same thing as 2 times 2 times 6, is it not? But that is the same thing as, I'm running into some other stuff here. That's the same thing as 2 times 2 times 2 times 3. Prime, 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 prime. Give me another one. Let's see if there's one on the list. 26. You got it. 26. Notice that 26 is equal to 2 times 13. Prime, prime. Give me another one. Give me another one. Hurry. 10. 10. 2 times 5. Prime, prime. 30. 30. That's 3 times 10, but that's equal to 3 times 2 times 5. Prime, prime, prime. Give me another one. 42. 42. Okay. Notice 42. Oh, that's 2 times the 21, is it not? But notice that that's really 2 times 3 times 7. Is it not? Is it not? It is, huh? So look, prime, prime, prime. 75, 76, yeah, you could do it for all of them. Any number that is not already prime, you can do this. This is called the fundamental theorem of arithmetic. That any composite number, non-prime numbers are called composite numbers. We call them composite because they are composed of products of primes, distinct ones. Isn't that cool? I said, isn't that cool? Yes. Jumping for math. Yes, there we go. Yes, that's right. It is cool. So cool. Yeah. Okay, good. So cool. Very good. All this because I wanted to show you what is the principal square root of 100. What is the principal square root of 100? Remember that? Long ago when I saw that thing and I was like, oh wait, fundamental theorem of arithmetic. Well, it's because we can do this game with the number 100. Yeah, people are saying 10. I'll show you why it's 10. It's because of the fundamental theorem of arithmetic. That's really 10 times 10. I could have broken it down further, but yeah, that's equal to 10 squared, which is 10. But fundamental theorem of arithmetic wise, this is really 2 squared times 5 squared as well. I haven't taught you this before, but this is a rule that when a radical is with a product of 2 numbers, if x is times y, the radical travels to x times y. This is true. Also, if you have x divided by y, it travels across the numerator and the denominator to give me radical x divided by radical y. Okay? So these hold true. This is called the product and the quotient rule for radicals. So applying that, we can do this as well. So this gives me 2 times 5, which, oh, you guessed it, that also equals 10. So potato, patata, tomato, tomato, it don't matter. Now, you might be thinking, well, this requires more steps. Why are you doing that? Do you just enjoy wasting chalk and time? No, it's not that. It's because sometimes you don't get a perfect square like 10, okay? Sometimes you just don't get a perfect square like 10. What if I had something like 14? What is the principal square root of 14? This is where the fundamental theorem of arithmetic is important. This becomes 2 times 7. So this is its prime factorization. So we know that it doesn't simplify any further. That square root of 14 is as simple as it gets. But what about, let's say, square root of 28? Let's use the fundamental theorem of arithmetic, which is a really fun game, really. I love playing this fundamental theorem of arithmetic game. Let's break down 28 to its prime factors. So that's really 2 times 14, right? Okay, so that's really 2 times 7 from above. But notice that the 2's can combine here to become 2 squared. And by the rule that I just erased, the radical can travel across multiplication. So then this becomes square root of 2 squared times square root of 7. And the square root of 2 squared, the radical just eats the 2. Because it's the square root, it eats squares. And all that remains is a 2 root 7. So this is why doing it via the fundamental theorem of arithmetic has merit. Because it allows you to find out what the square root of 28 is in perfect analytical expressions like 2 root 7. Of course, you could have put it in your calculator and it would give you the decimal expression. But we as mathematicians aspire to find what is its analytical expression. And you will be required to do this on your homework and tests. 2 square root of 7. Very good, Sonia. That's right. Pitfall. Square root of x plus y does not equal square root of x plus square root of y. Pitfall. Square root of x minus y does not equal square root of x minus square root of y. Do not make these mistakes. Here's an example. Square root of 3 plus 4, okay, versus, oh wait, that's not very clear. Okay, how about we do square root of 9 plus 16? Does this equal square root of 9 plus square root of 16? Do they equal? They're clearly not, because I'm telling you they won't. But I'm going to show you why you can't do this in general. Because look, the square root of 9 plus 16 is the same thing as the square root of 25, which equals 5. The principal square root of 25 is equal to 5. Principal, okay? And now the principal square root of 9 and 16 respectively is 3 and 4. So 3 plus 4 gives me 7. But if you travel across this equation, it's saying 7 is equal to 5. Class, does 7 equal 5? No, 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 no. Required to explain all of what you just did. Well, yeah, I mean, you have to show your work. Yes, showing your work is required. That's just how us educators know whether you understand what's going on. If you just give the final answer and you don't show how you did it, then we can't know whether you knew how to get there through a step-by-step logical reasoning. Where did the exponent 2 go with the square root of 28? Good question. So we got square root of 28. It breaks down to 2 times 14, which then breaks down to 2 times 2 times 7. But 2 times 2 is the same thing as 2 squared. And once the radical distributes to 2 squared times 7, I get the square root of 2 squared. So the square root undoes this 2 power. The square root undoes the square, leaving just the 2 all out here all on its own. If you take the square root of something squared, it undoes it. Aha, you are welcome. Moving on. So let's do an example. Let's do what we've learned here to apply it to something. Let's say I have 9x squared divided by 25y to the 4th. And I'm going to take the square root of the whole thing. Simplify that. Well, first we do the quotient rule. We distribute the radical to the numerator and to the denominator. Okay. Then, that was the quotient rule. The radical goes to the numerator, radical goes to the denominator. Now that the radical is up here and up here, now we can send it across the multiplication right here and right here. So now we use the quotient rule. Next we'll use the product rule. This equals square root of 9 square root of x squared over square root of 25 square root of y to the 4th. Okay? So the principal square root of 9 is 3. And the principal square root of x squared is x. The principal square root of 25 is 5. And the principal square root of y to the 4th is, wait a second, I don't know what it is. Let's think about it. Y to the 4th is the same thing as y squared times y squared, right? Right? Because remember from earlier, if a number with the same base and different exponents are multiplied, same base, different exponents multiplied, then their exponents add. So we were just doing the reverse process of what we were doing earlier. We took that y to the 4th and we take it in reverse to make it like this. Okay? The exponents add, right? So we're going in the reverse. Why am I doing that? Well, it's because this is a square root. And I want to distribute the square root onto the y squareds. You see that? Because now square root of y squared is y. So square root of y is just y, and we got 2 of them, so we got 5 times y times y. Might as well just write that 5 times y squared. And we'll call it a day. Oh, yeah, I love it. I love it when my students get that, oh, light bulb moment. It's as if your mathematics teachers and your mathematics education was never at this level, and you are just enjoying having lots of justification for what the mathematics was always talking about. Huh? Very cool. Yes. Yes. Let me know if you think that's cool. Nailed it. Yes. Let me know if what I'm saying is some truth. Say truth or say false. Truth or false. What he's saying is truth. 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 True. 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 Ha 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 ha. Good. True. Okay, good. Love it. All right. Now, let's add and subtract square roots. Let's do more arithmetic operations with square roots. So let's do like 5 square root of 24 plus square root of, I'm inventing a problem in my head right now, 7. Okay. Okay. Let's add these two expressions together. Okay. First, we have to utilize the fundamental theorem of arithmetic to break down this composite number 24 to 2 times 14 plus square root of 7. Just that comes along for the ride. Then we know that we still have some decomposing to do. This becomes 2 times 7 plus this square root of 7. That's why I was taking so long thinking of what to put here. You'll see why. It's because of this 7 right here. Then we got 5 square root of 2 squared times 7 plus square root of 7. Okay, bring the calculation up here. Notice that, like before, we can distribute the square root. And just like before, the square root of 2 squared is just 2. So this becomes 5 times 2 square root of 7 plus square root of 7. And then bringing the calculation over here, 5 times 2 is 10. So this is 10 square root of 7 plus square root of 7. And then you realize if I have 10 oranges and someone gives me another orange, how many oranges do I have? How many oranges do I have? Tell me. A bunch of oranges. No, Isaac. I'm looking for a number. If I have 10 oranges. Oh, 11, yes. If I have 10 oranges and someone gives me an orange, I have 11 oranges. Yep, 11. So this number goes from 10 to 11. And that square root of 7 comes along for the ride because the square root of 7 was behaving as the oranges. Does that make sense? It's probably making more sense now than it ever has. Yeah. Lost, why'd you add? Okay, Janice, the reason I added was because this plus sign has been here from the start. This plus sign has been chilling with us this whole time. Look, plus, 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 plus. And that's why I added, because that plus has always been there. For sure. Carrie Hughes. That's right. Faux show. Does that make sense, Janice? Doc, the square root had a 1 in it. I'm with you. Square root had a 1 in it. What? I'm really lost as to what that means. Look at the beginning. Why is it 11? What? I don't see what you guys are asking right now, but that's okay. I may figure out what they're asking. Where you said there's a 1 in the front of the square root. There hasn't been a 1. This is an 11. I mean, this is the only ones I see here. This is an 11. And it's 11 because it's 10 square root of 7 plus a square root of 7. So it's like saying if I got 10 oranges and someone gives me an orange, I have 11 origins. 10 plus 1.
In the beginning where it says 5 square root of 24, and then you broke it down to 2 times 14, shouldn't that be 2 times 12?
Oh, I see what you're saying here. That is correct. So this should be, and how can you talk to me like that?
I can unmute, but I can mute back. It looked like it was all getting confused. So
Who is this? Which one are you?
Joe.
You're Joe?
Yeah.
Okay, that's fine, man. Yeah. Oh, I was just like, man, I didn't think you can unmute yourself. What are you, a hacker?
No, not at all.
You just press some button. Thank you
Yep.
for catching that error. You are correct, class. 24 is really 2 times 12, not what I had. So this then becomes 2 times 2 times, so this is 2, so 12 is 2 times 6. I'm going to have to modify the problem. So then this becomes 2 times 2 times 2 times 3. Okay. So then we bring it over here. Okay. So then I get this is equal to 5 square root of 2 times 2 times 2 times 3 plus square root of 7. Okay. So now at this point, the only square I can get is if I combine 2 2's. Okay. So then this becomes 5 square root of 2 squared times, I'm just going to say 2 times 3 is just 6 now, because there's no more decomposition possible. The only reason we decompose it was to see if we can find some squares. And the only square we can ever get from this situation is a 2 squared. Okay? Because we can only combine a pair of 2's. Then when we distribute the radical, I get 5 square root of 2 squared times the square root of 6 plus the square root of 7. Okay? So then this reduces to 5 times a 2 square root of 6 plus square root of 7. This was an ill-advised constructed problem off the top of my head because I wanted this to have a 7 in there so we can add them at the end. But, you know, I'm getting kind of hungry. I need some food for my brain to work. I need some food. Help. So this becomes 10 square root of 6 plus root 7. I eat a lot. If you guys don't know me very well yet, but I have to eat a lot of food. I kind of have to eat every 2 to 3 hours or else I kind of like shut down. So thank you to Joe for randomly unmuting and talking to me. Could y'all hear him too? That's kind of cool. That's kind of cool. Yeah, honestly, that was really helpful that happened. But having all of you all be able to talk might be like a little difficult. And here's why. Here's why. Because I can't see you. And if you're all talking this and that, this and that, this and that, food. I may not be able to like handle it, if that makes sense. So if a situation like this happens and someone really knows something, feel free to do what Joe did. That was very helpful. The snacks, sensory overload. Yeah. Thank you. Yeah. As a mathematician, you'll find out that I'm not very good at arithmetic. Adding, subtracting, multiplying, dividing is not my thing. Even though I'm a number theorist, and you would expect that a number theorist is good at that stuff. As I told you earlier, math is not about multiplying and dividing really big numbers in your head. If you can do that, that's great. I'm sure you will impress a lot of people at a lot of parties. But that's not really what mathematics is. And that's not really what mathematicians do. I'm in a classroom. Do not so. I don't know what that means. Okay. Shout out to my lovely wife for throwing me them almonds. They're really hitting the spot. Everybody in the chat say shout out to Michelle. Everybody in the chat say shout out to Michelle. Shout out to Michelle. They're doing it. Yeah, she's saying shout out to all of y'all. Yeah, because I was not going to be able to keep teaching you. Michelle is killing it.
Keeping everything going.
Thank you. Thank you, sweet cheeks. Yeah, everybody's saying great job. Shout out to Michelle. All right. Here's an example that won't mess up horribly like earlier. Okay? 3 root 7 plus square root of 14. Notice that this will break down to 3 root 7 plus square root of 2 times 7. Okay? Notice that I can just do the radical like so. And now I can factor out a root 7. Okay? Now, does everybody know, or does everybody remember what it means to factor out? And if you don't, it's okay. I know not all of you remember it, right? Yes, not all of you remember what it means to factor something out, okay? This step was the part where I factored out a 17. Really, factoring out means when you have two terms being added to each other or being subtracted from each other that have something in common, you can take that part out, like so. Why does this work? Well, it works because if I distribute it back into each of the terms, I will restore this original thing on the left-hand side. See, look. I know what you're thinking. That's root 7 times 3, not 3 times root 7. You're wrong, Professor Niazi. You need a lot more help than almonds. Maybe you can't remember. Okay. Well, actually, the real numbers in the way in which we use them are commutative. Let me ask you a question. What is 3 times 4? 12, 12, 12, 12. I'm not telling all of y'all that there's cops around. Now, what is 4 times 3? What is 4 times 3? 12. Yeah. So does the order in which you multiply the two numbers matter? No. That's why root 7, 3 and 3 root 7 are the same thing. It doesn't matter. Potato, potato, tomato, tomato, it don't matter. Matter of fact, the fact that 3 times 4 is equal to 4 times 3 is a very simple-minded notion that us human beings believe. When you get close to the space-time curvature of a gravitational mass on the order of a black hole, mathematics and physics as we know it breaks down. And for all we know, 3 times 4 may not equal 4 times 3 inside of a black hole. Mathematicians study this kind of stuff. Yeah, Carrie, that's right. We have not invented enough mathematics to understand what happens inside of a black hole. And matter of fact, there is mathematics. It is scary because reality is totally different than what you would intuitively think if that's the case. Matter of fact, mathematicians already study mathematics where two numbers A times B does not equal B times C. It's a field called non-commutative fields and non-commutative algebra. It's a form of mathematics studied in abstract algebra, which is pure mathematics. This is the kind of mathematics you will get into if you pursue a PhD in math. We got Tony Stark as a teacher. Awesome. Nah, Tony Stark ain't as swole as me. He had to like make a suit to be swole. I'm cooler than him. I'm like Batman or something. He looks like Bruce. Laugh my something off. This professor is fit. Oh no, lit. Whatever. Iron Man is way better than Batman. Yeah? Well, why does he gotta make a suit to be cool? Professor Hulk. Nah, man, I'm small. I still have a lot of gains to make. I'm actually really tiny. This really like zoomed up version of me is like really like projecting a false sense of my swollenness. But anyways, back to lecture. Moving on to the next subject material. Better not skip legs. Oh my gosh. I'm about to choke on some of this almond right now. The pre-assessment is if you go into the modules, you just do the pre-assessment. You go to modules and click on pre-assessment. It's part of section 1.1. It'll send you to a website where you can fill out the pre-assessment. And I can't go over the pre-assessment. The point of that is to test kind of where you're at right now. It's not for a grade, but we ask of you to do it. Now, let's do a problem where we use radicals in the denominator. Let's just use numbers. 2 divided by 1 plus square root of 3. How can we simplify this? Remember, usually if you have a situation like 2 divided by square root of 3, you've been trained to rationalize the denominator. All throughout your mathematical experiences in like middle school and high school, they always tell you to rationalize the denominator? Okay, good. Gilberto, good. Okay. You're always taught to rationalize the denominator. The way you do it is you multiply by a fancy number 1. Anything divided by itself is 1. So doing this is really not changing the number. So I can say it equals what will end up. A square root of 3 times a square root of 3 ends up becoming a 3. And here's why. Square root of 3 times square root of 3 can be re-expressed as the square root of 3 quantity squared. Whenever you square something with a radical, you just get what's on the inside. So you end up rationalizing the denominator. Okay. Let's rationalize this denominator. Let's try and use that old trick of ours. Let's see if it works. Okay. Notice that this ends up becoming 2 square root of 3 divided by root 3 times the quantity 1 plus root 3. Okay. Notice that I have to distribute the square root of 3 to each of these terms now. Okay. This becomes square root of 3 plus square root of 3 times square root of 3. And remember from right here, every time you multiply square root of 3 times square root of 3, you get a 3. Just like every time you multiply square root of 17 times square root of 17, you get 17. It's because any square root times itself becomes the square of itself, which undoes the radical. So this reduces to 2 square root of 3 all over root 3 plus a 3. But wait, I thought our old trick was always supposed to work. Then why do we still have a radical in the denominator? Why? Well, it's because that trick doesn't work when you have a situation like this. When it's 2 entities being added to each other, it doesn't work. If it was just a pure radical sitting all by its lonesome over here, then yes, it works clearly. But if it's ever added to something or subtracted by something, this trick does not work. This didn't rationalize the dang denominator. It's not rationalized. So I have to introduce you to a new concept, a new technique. This is called the conjugate. This is a technique of rationalizing denominators. It's by utilizing the conjugate. Given a number a plus square root of b, its conjugate, I'll use an arrow to show you how the conjugate will transform this quantity on the left. A plus square root of b, when you conjugate it, becomes this, a minus square root of b. Just like when I conjugate a minus square root of b, conjugate, I would get a plus square root of b. You guys see that? This operation that has to do with radicals being added to other numbers is called conjugation. Let's now try that same problem we did earlier. What was it? I deleted it, but it was like 2 divided by 1 plus square root of 3. Okay. Something like that. It doesn't matter. Okay. Because all I want to practice with you guys here is how to conjugate and how to rationalize this denominator. Multiplying top and bottom by root 3 didn't work last time, remember? So how we do it is we multiply top and bottom by the conjugate of this expression down here. And really, it's just a fancy number 1. Because 1 minus root 3 divided by itself is 1, right? So 1 times anything is just itself. So we didn't change anything at all. I can say this equals what is coming down here. So this becomes 2 times the quantity 1 minus square root of 3. Don't forget that this parentheses needs to come along with it because the 2 must distribute to this term and the 2 must distribute to this term. Okay? So then this becomes 1 plus the square root of 3 times 1 minus the square root of 3. Okay? We will soon discover that this, once we FOIL it, will not have a radical. I'm really lost. Why? Which step? While you type it, I'm going to keep moving, and then I'll notice which step that you're asking. Okay? Now I distribute this 2. This equals 2 minus 2 root 3. And then I'm going to have to FOIL these terms. So 1 times 1 is 1. 1 times negative root 3 is negative root 3. Plus root 3 times 1 is root 3. And root 3 times negative root 3 is negative 3. Let's see if you have written what. I am confused with why you subtracted. This right here, this right here, this right here comes from this right here. This is the conjugation operation. If you sit type, yes, the top. Yeah. If you sit type, you'll see that this conjugation operation allows us to rationalize the denominator. Just wait until the end of the problem. You'll see that the denominator will not have any radicals in it. Matter of fact, the next step will show that. Negative root 3 plus a positive root 3, they cancel. So all that remains is 1 minus 3 in the denominator, which is a negative 2. And this is 2 minus the 2 square root of 3. Okay? So notice, I'm bring the problem up here and clear up some real estate. I can factor out a 2 and I get 1 minus root 3 all over a negative 2. Then I can cancel out the 2's and the negative distributes to each term. So I get negative 1 plus root 3 as my final answer. Okay? Guys, it is now 8:26. Class was technically over at 8:15. We had severe technical difficulties in starting the class. I believe we didn't even get started. The class starts at 5:45. We didn't even start until 6. And then we're still getting to understand some of the fundamental basics. Every semester, I start out slow because I like to fill in the gaps in people's minds about math. I fill in the gaps in the stuff in mathematics that they were not taught properly. And so we have started out the semester a little behind here because we're supposed to get through section 1.5 and we're halfway through section 1.3. So here's what I'm going to do for you. I'm going to provide you an extension, okay, on your homework and assignments. That way you have more time to understand the fundamentals of what we're talking about, and B, next class period, we're going to hit the ground running. Woo, yes, woo, yeah. So take this opportunity very seriously, because how well you understand what happens on the first day of class will translate to how well you do in the course, hands down, because mathematics builds upon itself. The exponent rule, the power rule, the quotient, how the radicals travel across multiplication and division, but not addition and subtraction. These concepts will come up every single day in this class, every single time in this class. On your first test, second test, third test, fourth test, final test, these concepts will be there lurking. And if you don't understand it now in the first week or two, when we add more material on top of it, you will start to drown. And that is what I want to prevent. I want you all to not drown, but I want you to be swimming in it like an Olympic swimmer, okay? So what I do is I prepare you for the swim. I teach you how to swim well. And by swimming, of course, I'm talking about doing the mathematics and the operations. So what I'm going to do is I'm going to provide you an extension just this once, and hopefully we get fully caught up, okay? But we are 15 minutes over the normal time that is supposed to be allotted for this course. And that accounts for the 15 minutes that it took for us to all get set up and into the Zoom meeting. So hopefully I can figure out how it will just automatically let people come in. I don't have to allow them to first go into the waiting room and come in like it's a doctor's office or something. This is a classroom. There's no waiting room. There's just a classroom, okay? Wait, what is the extension on? Okay, so because we did not cover section 4.1 and 1.4 and 1.5. We did not cover section 1.4 and 1.5. That was on the schedule for today. So because we didn't even talk about that, I'm going to provide you an extension on all assignments having to do with 1.4 and 1.5. In 1.3, we're about halfway through it. And there's some stuff that we have not covered that is in your textbook that you can teach yourself. A lot of college is about teaching yourself. You will not always have a teacher that goes to a high level to help you learn. And so, although I am like that, I'm spoiling you. This is not how it always is. So what you got to do now is teach yourself some of 1.3, all right? I will still lecture over 1.3, and I will still extend 1.3. But I want you to start teaching yourself some 1.3 after you've mastered 1.1 and 1.2. Okay? Go do the homework problems and the assignments and go through the textbook, because the textbook is a very good resource and it has a bunch of problems and solutions so that you can learn. Okay? Zoe, thank you. You're very welcome. We can ask you questions though, right? Yes, you may email me questions, but unlike this interface, you may not get an answer right away. I'm a busy person, and I may answer you maybe like sometimes in like 12 hours, sometimes in 24 hours. Hopefully it never exceeds 24 hours, but it might take some time for me to answer you. Okay, so what I like to do is teach my students how to fish. That way you can catch your own fish. And that's what I'm doing right now by thoroughly going over all the rules and explaining why things are the way they are. And when I throw added information like why you can't divide by 0 and the fundamental theorem of arithmetic, that stuff isn't going to be on your test, but understanding that stuff is imperative for you to really get how to do these problems. Okay, so me doing all these things is to add extra investment in your mathematical abilities. So when I add that extra investment, if you take it seriously, if you go now and go work really hard, work every day, very, very, very hard, dedicate yourself to this course and to the material, you will learn and grow, okay? But you have to work hard starting right now. You can't think, well, I'll work hard later. Mathematics is fundamental. It's all built off of the fundamentals. The beginning is the most important part. So right now, it's the most important part of the course for you to have to work really hard and master it as soon as possible, okay? Yes, I will answer your questions via email, but they won't be immediate like it is right now, okay? I will provide you extensions for 1.3, 1.4, and 1.5, even though we went halfway through 1.3, okay? If anybody has any questions, speak now. And if not, I will see you guys in a week. We can make a group on group. Yeah, sure. Make that group. Yeah, you guys, there's nothing saying you can't collaborate and talk with each other about the homework and help each other out. That's a wonderful way to learn, is by collaboration. But make sure that you understand it yourself as well. Make sure if someone gives you a hint or shows you how to do something, you then go do 10 problems like that without hints, without help. Okay? I expect a lot out of my students. I expect the utmost amount of dedication and hard work from all of you. All right. I'm gonna give it about 1 more minute. If nobody asks any final questions, I'm just let it go for an email situation. Yes, we meet every Wednesday online at 5:45 p.m. until 8:15 p.m. You are very welcome. Yes, we only meet once a week. You're very welcome. Okay. Well, if anybody has any questions, send me an email. For the rest of you that are in here, have a good night.